define a word, namely implementation tuning. And what we mean with that is manual application of code transformations, that is optimizations or tuning, and which current state-of-the-art optimizing compilers cannot perform automatically. So what is regarded as implementation tuning this year may be regarded as complete waste of time next year. That means if compiler technology is capable of doing something, then we shouldn't do it manually, of course, since hand-optimized code is almost always more complicated to write and to read, and therefore also to modify. Okay, so it is much better to let the compiler do the biggest part of the work. So this is an algorithm for improving the performance of a correct C or C++ program. First of all, if the performance is good enough, then you can go on vacation instead, or at least do something else. And what we should not do is to guess what takes time. It's usually quite difficult to guess that properly, and it's really a bad approach to optimize code, to sit and guess. What we do as engineers is to measure, to collect data, statistics, which says this part of the program takes this amount of time. Okay, and then we can focus on what takes most of the time. Okay, it's not always so simple, so to speak, that if, for instance, square root, there is a library function called sqrt, which computes the square root. If that function takes most of the time in your program, then the first approach is not to optimize the implementation of square root, but instead to think maybe you can avoid calling square root so frequently. So if we profile in step 2 and find that some part of the program takes most of the time, the automatic next step is not to optimize just that part, but instead to think if we can either optimize that part, or it may look as a bad idea, such as it's already very optimized, and instead use it in some different way. Okay? So if we now have figured out what is the most time-consuming part, what can we do? We can go through this checklist and see if we get some idea. First, the simplest may be to switch from GCC to Clang, or from Clang to GCC, or to IBM's or NVIDIA's or Intel's compiler, if we have a platform with Intel compilers. Intel's compiler is also very good. Okay, so that's one. That's a really simple option. And if we cannot switch compiler, we can at least try different compiler flags. Okay, so that's like 10-minute check, and then rerun at most 10 minutes maybe. Okay, if that doesn't work, some other idea, I mean, if it isn't good enough, we maybe can change an algorithm or a data structure. the most important thing that we should look for is how to make the common case faster. And that's very obvious, since the common case typically is what takes most of the time, since it's common. So if we can understand that there are some special characteristics of the input, or actually of the most frequent input, that we can exploit using a faster algorithm which requires certain properties of the input, or if we can pre-compute or cache certain values, or can we use mathematics to simplify the program. For instance, if we compare distances, maybe we can skip using square root to find the distance and compute something mathematically equivalent when we sort distances. Okay, that's a good start. And can we use well, how can we get these insights? We can. What we want is to understand how the behavior of the program affects performance. So, to understand the behavior of the program, we want to know where does it spend most of the time. But we also want, on a more higher level, to understand the behavior. For instance, if we conclude that some part of simplex takes a lot of time, maybe it's possible to avoid calling simplex so frequently in the branch and bound. Okay? Is it possible to select a different vertex so that simplex reaches the optimal solution quicker? That's a separate issue. I mean, first we may want to avoid calling simplex so frequently by selecting a node in a clever way, or we may want to make simplex faster, either by tuning the implementation of each function, and also by selecting a different vertex, perhaps. That's just a suggestion. Okay, so then what we do is to try to get ideas. Now, this is really a very small engineering research problem that we want to solve. So we should look for phenomena that we can exploit to make the program faster. Examples of phenomena that we can discover, or well, not discover, I mean it has already been discovered, but the cache memories, that's a typical thing which illustrates this, that there is temporal and spatial locality, and then somebody invented cache memories in the 1960s. Okay, are there similar aspects of your program that you can exploit to make the common case faster? This is a really creative and fun part of writing efficient C code. And then we implement the ideas, measure if they affect performance. If they do, in a good way, then we run big tests to see that all the previous test cases still work. And go back to part one. This method can, of course, be used to make a program faster, to make a single-threaded program faster or a multi-threaded program faster, or to make the program smaller. It's a more deterministic process to make a program smaller than making it faster, because often if we can figure out how to remove, or not remove them by ourselves, but so that the compiler can remove certain instructions in RPN, Word and Poly, then that usually does not make some other part of that function bigger. So we can usually improve one part, and the result will be an improvement in total. For performance, that's not always the case. Maybe we can make, for time, execution time, maybe we can make one part faster, but that may make some other part slower. For instance, that the cache memory behaves differently. And for multi-threaded programs, it is much more difficult to optimize for execution time.